In a groundbreaking discovery, NASA's Voyager spacecraft has crossed the edge of the solar system, encountering a startling and mysterious phenomenon, a fiery, high-temperature wall just beyond the outer reaches of our cosmic neighborhood. This phenomenon, described as a wall of fire, was recorded in a boundary region known as the Helopause, the area marking the transition from the solar-dominated region to interstellar space. However, what exactly did the Voyagers discover, and what is this area? Let's delve deeper. Back in 1977, in an era when computing power was minuscule by today's standards and space technology was only taking its first confident steps beyond Earth, NASA embarked on a long, almost unthinkable journey. Two modest-looking probes, Voyager 1 and Voyager 2, were launched with a mission to explore the outer giant planets, but their true purpose lay much further afield. Their mission was to reach the very edge of the solar system and break through into the unknown interstellar void after decades of space travel. Powered by tiny radiothermal electric generators and controlled by Earthbound teams that communicated across vast distances, these veteran spacecraft made a revolutionary discovery. They encountered a surprising and unexpected obstacle, a giant, invisible to the eye but fiery in nature wall of extremely high temperatures. This boundary, known as the Helopause, is much more complex and dynamic than just a line on a map of space. It marks a dramatic frontier, a clash of two powerful forces. On one hand, there is the constantly blowing solar wind, a stream of charged particles, mostly protons and electrons, flowing out of the sun in all directions at speeds of hundreds of kilometers per second. This wind forms a huge protective bubble, the heliosphere, round our star system. Imagine a bubble in a river stream, only on a cosmic scale. The solar wind blows out this bubble, pushing aside the surrounding interstellar medium, the thin gas, dust, and cosmic rays that fill the space between stars in our galaxy. The heliosphere extends incredibly far. Its nose, in the direction of the sun's motion through the galaxy, is about 3 times the orbit of Pluto, and its tail extends even further. The Helopause is that critical surface where the pressure of the rapidly weakening solar wind finally equals the pressure of the oncoming interstellar medium. This is not a static wall, but a turbulent transition zone where intense interaction occurs. It was here, on this frontier, that the Voyagers made their discovery. Instruments such as a plasma detector and a cosmic ray sensor recorded changes in the direction of particles, the composition of the medium, and a colossal jump in temperature. The readings soared to staggering levels up to 50,000 C. This phenomenon was metaphorically called a wall of fire or a wall of plasma, or perhaps it's more of a dome, in any case. A natural question rises: how can such extreme temperatures exist in the vacuum of space? And why didn't the probes, made of metal and electronics, melt instantly like cheese in a microwave? The key lies in understanding the nature of temperature in space. Temperature here is primarily a measure of average kinetic energy, the speed of movement of particles, not heat in the usual sense, as from a fire or heater. The density of matter there is trillions of times less than in Earth's atmosphere at the surface. Therefore, despite the phenomenally high temperature that is, the speed of individual particles, the total amount of thermal energy they can transfer to the spacecraft during their rare collisions, is extremely small. It's like being hit by rare drops of water flying at great speed. You'll feel the impact, but you won't boil in sweat. The design of the Voyagers took into account the extreme conditions of space, including vacuum, temperature changes, and the sparse but energetic environment of the Helopause. This careful engineering became their salvation from instant destruction. This temperature jump is a direct consequence of the formation of a so-called shock wave, or more accurately, A penetrating shock wave. When the supersonic solar wind encounters the interstellar medium, it is suddenly slowed down, much like air in front of a supersonic aircraft creates a shock wave. In this case, the kinetic energy of the wind is converted into thermal energy of the particles, heating them up to tens of thousands of degrees. This complex interaction creates a zone of intense turbulence and high-energy particles. But the Voyager's discoveries did not end there. As they crossed the Helopause, they carried with them not only particle detectors, but also ultra-sensitive magnetometers, and here, another surprise awaited researchers. It was expected that when moving from the heliosphere to the interstellar medium, the orientation of the magnetic field would change dramatically, since the Sun's field should give way to the galactic magnetic field. However, the data from Voyager 1 and later Voyager 2 showed something different. It turned out that the magnetic field immediately beyond the Helopause maintained a direction very close to that of TH. A magnetic field inside the heliosphere. It was an unexpected alignment. Initially, there was uncertainty with the data from Voyager 1. Was this a local anomaly or a general pattern? But identical measurements by Voyager 2, which crossed the Helopause at a completely different point in space, tens of astronomical units to the south, confirmed this amazing fact. The magnetic field of the interstellar medium near the Helopause turned out to be co-oriented with the solar magnetic field. This discovery required a revision of theories about the structure of magnetic fields at the edge of the solar system and their interactions, pointing to a more complex and possibly large-scale organization of the interstellar magnetic field in our local galactic environment. Now, the significance of the Voyager mission goes far beyond simply establishing the existence of the Helopause and measuring its parameters. They provided the only direct measurements of conditions in this remote and difficult-to-reach region. Every bit of data transmitted over a distance where a radio signal takes more than 20 hours to react. Earth is priceless. These data have radically changed our understanding of the structure and dynamics of the heliosphere, our cosmic cocoon. The heliosphere plays a vital role as a shield, deflecting galactic cosmic rays, ultra-high energy particles that can be hazardous to both space technology and potentially to life. Studying how this barrier interacts with the interstellar medium, how it is formed, and where exactly its boundary lies is of great importance for astrophysics and HELIOPHYSICS. As it turns out, the amazing wall of fire is a vivid testimony to the powerful processes occurring at the border of two cosmic environments, as the Sun's energy is transformed and dissipated at the very edge of its influence, and the unexpected alignment of magnetic fields opens a new chapter in the study of the magnetic structure of the local interstellar space surrounding our solar system. Now, almost half a century after their launch, these small messengers of Earth continue to work, transmitting unique data from interstellar space, where no man-made object had previously ventured. The discovery of the fiery wall and magnetic surprises at the Helopause is not an endpoint, but a powerful impetus for future research such as the IMET mission, which will specifically study these boundary processes at close range, building on the legacy of the Voyagers. Although the spacecraft will be much closer to Earth than the Voyagers, its purpose is directly related to understanding how our solar system interacts with the rest of TH. Cosmos. This mission will observe the boundary of the heliosphere, the region where the solar wind collides with interstellar matter. This is where outer space begins in the full sense of the word. IMEP will operate at the L1 Lagrange point, approximately 1.5 million kilometers from Earth, on a direct line between our planet and the Sun. This will allow it to continuously observe the solar wind and other particle streams without interference from Earth's magnetic field, unlike the Voyagers, which moved in a straight line away from the Sun. IMUP will observe from a fixed position, collecting data using a complex system of sensors and spectrometers. The main objective of the mission is to create a detailed map of the interaction between the solar wind and the interstellar medium. To do this, the spacecraft will measure the flow of energetically charged particles, so-called energetic neutral atoms. These atoms are born in the boundary zone between the solar and interstellar environments and carry information about how the boundaries of the heliosphere are formed and changed. In essence, it will function like a cosmic X-ray, creating a three-dimensional model of the protective bubble surrounding the solar system. In addition, the mission will help scientists understand how particles accelerate in space. This has implications not only for fundamental science, but also for the practical safety of future manned missions. High-energy particles of cosmic origin can be deadly for both travelers and spacecraft. Despite its relatively close proximity, IMUP will operate in high radiation and variable space climate conditions. So, the spacecraft is equipped with radiation-shielded electronics and a passive thermal control system. It won't experience extreme temperatures like the 50,000 Celsius found near the Helopause. But it will still have to withstand the swings between the hot, sunny side and the cold shadow, as other probes have done before. In this way, IMAP is the heir of the Voyagers, their scientific descendant.